Hello, my name is Vineet Venugopal. This video is a walkthrough of the literature extraction pipeline developed and used in the Olivetti group at MIT. The pipeline is part of our effort to collect and structure scientific literature from multiple sources and use it for downstream tasks such as AI models, knowledge graphs, and search systems, etc. The first version of this model was created in 2019 by Eddie Kim. Since then, however, the field of natural language processing has progressed significantly so that we deal with large language models and other large scale AI extraction and information processing systems that did not exist at that time. Consequently, the latest version of the pipeline is more modular, is simpler, and incorporates a lot of the data engineering requirements of modern LLM and agent based frameworks. The video is split into four main sections. The first one deals with running the pipeline using the shell script. This is what you would use to download and add papers to the database. The second is an image schema of the pipeline and how it works. It's good to have this to understand why the pipeline operates the way it does. The third is a Jupyter Notebook walkthrough of the MongoDB databases that we have. How do we extract information, add information, and so on. And finally, the last section is a GitHub walkthrough of the GitHub repository, which contains information on the scripts that are used, the environment used to run them, how exactly do you implement them in your own system, as well as a detailed description of the current state of the database as a snapshot, as well as some tips and tools to run the database successfully. So let's dive right into running the pipeline. So I'm now logged into Spatula. Uh, Spatula has two main uh, directories. There is the home directory that contains the main synthesis databases, synthesis generation, etc. And there is also the data directory that contains all the folders where the data, the raw data, is actually stored. So the images are in the images folder. The Crossref database is in the Crossref folder, and the synthesis project contains a folder called files that has all the HTML's database, HTML's PDFs, etc. And Scratch contains all the documents that are temporarily saved in Scratch. So if you let's clear the screen. So if you go to home and then you go to Jupyter, you can see everyone's files here. Uh, the all the pipeline scripts are in the folder called, no surprise, pipeline. So if you go to the pipeline folder, you will see the three uh, Python files: search, download, and parse. Plus the environment that we use to run this is saved as a YAML file. You will also find this in the GitHub folder. But right now, you don't need to install it from the YAML. Instead, I have already created for you. So the environment is called pipeline env, which you can activate. So right now we are in the pipeline env. This is a lightweight pipe environment that contains just the required files needed to run the pipeline. Let's clear this again. So now we are in the right folder and we are at the right environment. So let's do a search on, let's say, plastic. So you would first, since this is a .py file, you have to run it from the Python pipe. So Python search.py.
and the search.py takes an argument called keywords. Oops. So let's say I specify biodegradable and plastics. You can either give it separately or you can give it together, depends on how you design your keywords. And let's restrict it to 100 documents per um, database that we are searching. So since we are searching through dimensions, lens, and crossref, it should ideally return 300. So now when you run it, it shows that the login for dimensions has failed, but this is to be expected because right now, as of May 2025, there is some problem with the dimensions API that the library is trying to figure out. Hopefully, this would be solved by the time you are watching this. If not, it doesn't matter. It will still go through Lens and the Crossref as you are seeing right now. So it's extracting a total of 199 records. 32 of them have been found to be duplicates, so they have been skipped, and these have been added to the Scratch folder. Okay, now that they have been added to the Scratch folder, the next step is to run download.py. So once you run the download, again, it should initialize all the classes. Everything would be, all the API keys would be set. And you can see that it's running something in the background. So when it runs download.py, what happens is that it's actually going to run all the records in Scratch for which the download is false. And right now, there are some 1 million records that need to be downloaded. Some of them are giving errors because they are from Wiley and Wiley only downloads PDF. So there must be some error with those documents. If you wait for a bit, you will see that this starts downloading. So I'm going to let the download continue separately. Instead, we can now do the 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 parse file parse.py. And once again, it will go to Scratch, get the record of all the documents for which the parse is set as false, and it's going to run this now. So right now there is some 946,000 documents that need to be parsed. And as you can see, it's running the parse on all of them. If there is an error, they are added to the scratch.errors later on. So that's it. That's really as simple as that. That's how you run the pipeline. You have these three simple commands. Once again, let's clear this. So the last one is parts.py. Before that, there's download.py. Before that, there's search. Please remember to always be in the pipeline env environment, and you need to be in the home Jupyter pipeline folder for this to run correctly. To have a schema of the pipeline while you run it. So in general, a user starts with a list of keywords about the papers that he needs to download. So let's say the user wants to download papers on high entropy alloys. The list of DOIs could be high entropy alloys, HEA, entropic alloys, and so on. This list of DOIs is given to the search.py module, which goes into the Crossref database, the lens database, and the dimensions database to retrieve a list of DOIs, which is then compared against our database to see if any of them already exist in our systems. And if not, we retrieve a list of DOIs that is the output of the search.py module. This list of DOIs is added to a temporary MongoDB database called Scratch, and two new fields are created for it by setting downloaded and parsed as false, since the record for the DOI has neither been downloaded, neither has it been parsed. We have only identified that this DOI needs to be downloaded. The next module in this list, which is the download.py module, goes to Scratch, retrieves all the records for which the downloaded is false, and then downloads it using specific publisher APIs and different agreements. Uh, and the HTMLs, PDFs, and XMLs downloaded through this is added to a different temporary folder. At the same time, the record for these DOIs is updated in Scratch by setting downloaded is equal to true. And finally, the parse.py module goes to Scratch, retrieves all the records for which parsed is set as false, and then parses them using parsing script for specific publishers. The fully parsed records are added to papers, and after changing parsed as true, the records are moved from Scratch to metadata after setting parsed as true, as I've already said. So as you can see, the pipeline is really modular in that the download.py module and the parse.py module only really interact with the Scratch module. It doesn't really interact with the search.py. And the advantage for this is that different users can run different search queries at different times, and anyone can do a download or the parse at any time. Or we have also set it up so that the download and the parse scripts run every other week automatically. So any records in Scratch that has not been downloaded or parsed will be downloaded or parsed respectively in about 2 weeks. Further, as you will see when we discuss different publishers, some publishers now don't allow us to directly scrape from their website. Instead, we give them a list of DOIs and they send us a bunch of HTMLs or XMLs from which we parse directly. So in that case, it is helpful to directly start the record from the Scratch module, because we just insert the records into Scratch, we specify where the files are specifically located, and when we run the download.py, it will automatically be added to our pipeline. So this ensures a smooth way uh, as well as a simple way of dealing with different publisher requirements and specifications. So let's do a quick demo of the MongoDB pipeline. The way we interact with MongoDB using Python is by using a Python wrapper called PyMongo, which provides us with a Mongo client that connects with the database from the Python server. So we first define the client, and the way the databases and the records are structured in the client is that under each client, there are a number of databases, and inside each database, there are a bunch of collections, and inside each collections, there are records, and records are the files that we need to retrieve. Each file has a unique ID. This could either be the JSON ID that's provided by MongoDB by default. It could be something we define, like the DOI of a paper. But there's usually a unique field that helps us to identify and retrieve that unique record. So if you want to see what are the databases that are available in the Mongo client, and this is specifically the client that's attached to the Spatula server, you just need to do client.list database names, which shows us the list of all the databases that are available here. So we see climate, crossref, images, metadata, papers, patents, scratch, title, abstract. Other ones like admin, local, test TV, etc., are not really relevant for us. And once you are inside each database, you can find out what are the names of the collections by by typing in client.database_name.list collection names, which gives us a list of collections that are in that particular database. So in this case, for climate, we see that there are 4 databases that are under climate. However, if you were to look at another database like papers, for example, we see that there's only one collection under papers. And if you are in a collection, you can look at the total number of records in that collection by typing in client.db.collection.estimated document count, which gives us the number of documents in that particular collection. So this is the script here. It shows us a way to go through all the databases and find out the number of records in each one of them. So with Crossref, we see that there are 143 million records. Images, there are 2.6 million records. Metadata has 12 million records. Something similar for papers. There are around 120,000 patents, 200,000 in Scratch, and around 10 million in the title abstracts. We also see that climate doesn't have anything right now, and that's the way we ran the code, where we assume that each database has a collection called records in them, which is not true in the case of climate, as we saw earlier. So if you want to see what are the number of records in the climate database, you would need to call each one of them separately. So let's take a look. We look at the number of documents is by doing client.db. So let's go to client.climate, and under climate, let's go for the papers database. So we see that that has around 11,000 records right now. And of course, these databases are constantly being updated, so the numbers keep changing. But this is a quick way for us to look at the information. Now, if we go through the databases one by one, uh, one of the best commands that's available in the MongoDB database is the find one command. So if you do client metadata dot collection find one, so this, by the way, you could either do client dot metadata dot records, or this is actually equivalent to client metadata records dot find one. So you could either write it like this, or you could write it like this. This is sometimes easier when you need to do nested loops for some operation that runs across many different databases and collections. But for now, this is a good one. So if you do client.records.find1, it pulls a random sample from the entire collection. So this gives us an example of what a metadata looks like. This is the ID that is assigned by MongoDB. This is the DOI of the record. And the metadata collection, as you can see by taking a look here, it contains a metadata of each publication. So it has details like the title, it has details like the journal, issue, volume, year, number of references, subtype, etc. It also has details about where exactly the file is stored in our system. So in this case, the HTML path is in the data folder of Spatula, in the synthesis folder, in the file subfolder, in the HTML subfolder, and is stored in this way. Uh, so even though it shows a PDF path, note that have PDF is false. So even though a PDF path has been created for it, there is no PDF file, there is no XML file, on the other hand, have HTML is true, which means that we actually have the HTML file for this particular DOI. Or in other words, this file was saved in the HTML format. So we will talk about what are the different ways in which files are saved for different publishers in a later part of this presentation. In general, only Wiley is stored as PDFs. Everything else is saved either as an HTML or an XML. It also has details like whether the download is successful, whether the download was attempted, whether it was parsed, and so on. Uh, most of these fields are available for most of the records. Sometimes, uh, for example, the open access field may be unavailable for some records, but generally most of these records are available for most of the records. The second database is title and abstract. As the name suggests, this contains just the title and abstract of all the papers that we have downloaded. So in this case, the DOI is given, the title is given, and the abstract is given. Uh, the information that's available in the title and abstract database is easily available also in the papers database, but we have had many instances where we just need the abstract and the title for some paper, and I found it easier just to save them separately in a different database because this makes it the whole process a lot faster. But it's not really necessary and the data is redundant. So in the future, if you think this is unnecessary, feel free to delete it. You might get some extra space in the MongoDB database. And finally, papers is the big collection that contains an entire paper. So if you look at the papers collection, it has the DOI, it contains the title, the abstract, and all the full text of the paper is saved in a separate field called paragraphs. And if you were to look at paragraphs, you see that the paragraph is actually a list of dictionaries. So if you take the very first dictionary in this list, you find just one paragraph. It has been identified as an abstract. If there was a supersection, you would have seen it here, but in this case, the supersection, there's no supersection. So the section name and the supersection name are the same. We used to capture a lot more information about these paragraphs before, whether they dealt with a synthesis related topic, for example. We don't do that anymore. We just do the text and the section name. You can look at the total number of paragraphs by looking for the length of the list. So this paper, for example, has 31 different paragraphs. Uh, so if you want to find the metadata for this particular paper, what you would do is you would first extract the DOI, which is a field that is shared by both the papers database and the metadata database, and then you would extract the metadata for this particular DOI. So that's how you relate the information that is present in these different databases. Now, images, on the other hand, this collection only contains the extracted images from around 2 million Elsevier papers. So again, we find the DOI, there's the journal, there's the year, the number of images that is found in this publication is shown here, and the images themselves is again a list of dictionaries. So if you were to look at the images list, and let's take the very first image. For each image, we have a label, which is whatever this image was called in the corresponding paper. Then the caption of that image, the URL for that particular image, the path in the database where this is saved, the number of the dimensions of the paper. So these are the height, width, and the number of channels for that image. And this one doesn't matter. This is about something I did one time and never did again. In general, if the dimensions is 0, 0, 0, it means that we have been able to extract the figure caption and the label for the image, but we have not been able to download the image itself. So if you look at the actual number of images that were downloaded, there are some 19 million images from these 2 million Elsevier papers. Finally, Crossref is the big database from Cross-reference of all the records that they have indexed from 2000 to 2022. Uh, when I created the database, only this much information was available. They make a yearly download of all their relevant data. So in the future, we might keep adding to this information and the latest year might keep increasing. So the Crossref database is really similar to the metadata database, except that we get a lot more information of each paper. So we get a lot more of the actual metadata that is related to each publication. We get the authors, we get the references, we get their titles, their citations, and so on. The metadata for in the Crossref database is usually provided by the publisher, who is then assigned a DOI. So this is as authentic as it gets for most publications. The Crossref database is huge; it's some 140 million records. If you look for the data in Crossref, it's identical to going through the Crossref API. We have been using the Crossref database a lot to look for new papers based on keywords, etc., which we have already described when going through the search.py document. Let's take a look at the GitHub for the pipeline that contains the code as well as the descriptions. So you will find the repository under the name pipeline new. So if you go to pipeline new, you can see all the scripts. The README file has a description of the structure for the pipeline. It contains a description of the three main modules, as well as detailed instructions on how to activate the pipeline as well as to run it. It also has information for external users who are outside of the Olivetti group, some documentation information, as well as notes on the usage. So if you go to the scripts, you can see the three main modules in their full detail. So if we go to search.py, for example, it contains the description of how the code to get the information from the different sources. You can see the main classes, etc. So if you want a deeper dive into how the code works, please feel free to go to the search.py, the download.py, as well as the parse.py modules. The adjoining wiki that you see here has a detailed documentation on how the pipeline works, what are the different publisher access policies, what are the different MongoDB databases, a description of all three of the modules, and some best practices and the database snapshot. So if you go to the overview module, you can see the description of what is the purpose of the pipeline, how it works, and so on. If you go to the outline contains the schema that we discussed earlier. It tells you what each stage is doing, what are the asynchronous operations, and what is needed from the user. Then if you go to the publisher access policies, you can see what are the current, as of May 2025, access policies of different publishers. For example, with Elsevier, it says that it provides HTML output, but MIT access is limited to pre-2019 content. ACS previously allowed with a signed TDM agreement, but bulk access is under dispute. You can contact the library if you need more information. The MongoDB databases and collections is a description of what are the different databases in MongoDB and what type of data and records does it store. What are the sort of information that you find in each of these records. Uh, Search.py module is a clear explanation of the different APIs that we use for search. It has a description of the workflow, as well as what are the changes that is made for each record. Similarly, download.py is a description of what are the different publisher APIs that we use for the download, what do we do for manual upload, etc. Finally, the third module is parse.py. It contains descriptions of the different parsing scripts that we employ. You can read through this for more information. The database snapshot, this is interesting. It contains a description of what is in these records as of May 2025. So it begins by a description of the number of records in each of this. Then we have a description based on the publishers. So if you look at the pie chart, you see that of the 12 million records in our system right now, around 49% are from Elsevier, 23% is from Springer, not including the 3.2 from Springer International. And the others are all less than 3 to 4%. So Springer and Elsevier forms the bulk of the downloads in our database. You can see the top journals based on their publications, scientific reports, notes in computer science, the year-wise distribution of what are the journals based on the year of publication. So it would be good to keep updating this on a yearly basis, but this is the record for 2025. And finally, if you go to the best practices and troubleshooting section, you will see some details on what are the highlights. And I'm hoping that this is also somewhere where we can keep a track of what needs to be done going forward.